Hello students, in this video we'll define the convolution of two functions, see some examples of how to compute them, and discuss the relationship with the Laplace transform. For two functions, f of t and g of t, defined on 0 to infinity, we define their convolution by f star g of t is the integral from 0 to t f of t minus s g of s ds. The convolution, so this integral over here, is a partial s integration. So this is a partial integral with respect to s. When we perform the s integration, I will have t's in my final answer. So indeed, f convolution g is going to be a function of t. So this is read f convolution g. So one thing we can note about this convolution is that if we let's look at this integral over here and change variables. If we let u be t minus s, then du is going to be negative ds. When s is equal to, so when s is equal to 0, that says that u is equal to t. And when s is equal to t, that says that u is equal to 0. And doing this, we see that our integral with this u substitution will become the integral from t to 0 of f of u, and then g of t minus u, and then I will have a ds, which is negative du. And I will flip the limits of integration with this negative sign and see that this is exactly equal to the integral from 0 to t of f of u g of t minus u du, which by the definition of convolution is exactly the same thing as the convolution definition, except with g first. So this is going to be g convolution f of t. So this implies that f convolution g of t is g convolution f of t, and this is our relationship that says that convolution is commutative. Doesn't matter which order you do the convolution in. So now let's see an example of doing convolution. Let's find f convolution g of t if f of t is equal to t and g of t is equal to t squared. So what we can do is we can say that f convolution g of t is g convolution f of t. And now it won't matter in which order I do the convolution. So I can write this as the integral from 0 to t of g of s. Well, the easier g of s to do would be g of s equals t squared. So we'll put a s squared over here. That's my g of s. And then I'll need an f of t minus s. So that will be f of t minus s will simply just be t minus s ds. This is my f of t minus s. And so now if I distribute this through, what we will have is we'll have that this is equal to the integral from 0 to t of s squared t minus s cubed ds. Again, since this is a partial integral, we're going to treat t as a constant. So an antiderivative of s squared t with respect to s is s cubed over 3t. An antiderivative of s cubed is s to the 4th over 4 from 0 to t. And those are s values. So this is s equals 0, and this is s equals t. When we plug in s equals 0 to this formula, we get 0. So all we need to do is plug in t. So if I plug in t, I'm going to get t to the 4th over 3 minus t to the 4th over 4, and that will be t to the 4th over 12. And while we haven't seen this yet, it can be shown that if I do the Laplace transform of f for this function and multiply it by the Laplace transform of g, we will get exactly the same thing as the Laplace transform of the convolution. And so we will see in future videos that this property, that the convolution Laplace transform is the product of the Laplace transforms, is an essential property in the theory of Laplace transform theory.